Imagine the ultimate architectural dream, a sleek, modern skyscraper designed to generate 100% of its own power. Historically, adding solar to a structure meant bolting heavy panels and clunky racks onto an already finished roof, a method known as Building Applied Photovoltaics. To eliminate that bulky hardware, engineers developed Building-Integrated Photovoltaics, or BIPV, where the building materials themselves produce the energy. The solar cells are hidden within the structural elements, replacing ordinary roof tiles, wall cladding, and even tinted windows. This integration turns solar power from an afterthought into the foundational structural centerpiece of modern design. This line plots a massive economic shift. The BIPV sector is on a rapid growth trajectory, projected to reach a $68 billion market value by 2030. These structures provide a direct path for high-density cities to reach net zero carbon emissions. However, wrapping a building in a live electrical grade creates a specific physical vulnerability. Fire protection engineers at organizations like FM Approvals are now investigating a critical risk. What happens when the exterior skin of a solar skyscraper catches fire? The environmental reward of this technology currently depends on solving a high-stakes engineering challenge. To see the hazard, we have to peel back the facade and look at the underlying cavity wall engineering. The outermost layer is a silicone solar cell protected by two solid sheets of tempered glass. Holding that cell in place are very thin layers of plastic encapsulants, like ethylene vinyl acetate, which are highly combustible. Directly behind that glass is a 2 to 6 inch air gap for ventilation, followed by the building's insulation and a network of interconnecting electrical wiring. Every BIPV wall functions as a complex, layered ecosystem that packs fuel, air, and ignition sources into a single structural unit. To observe how this ecosystem reacts to heat, researchers use the 16-foot parallel panel test to simulate a severe exterior fire. The test reveals a specific sequence of failures. First, extreme heat causes the outermost tempered glass to shatter and fall away. Once the glass completely breaks, the highly flammable plastic encapsulants inside are suddenly released and exposed directly to the roaring flames. This triggers a chimney effect. The physical air cavity behind the panels sucks the flames upward, rapidly accelerating the fire as it feeds on the internal cables and adhesives. Without precise engineering, the physical air gap designed to cool the building effectively weaponizes an exterior fire. Beyond the physical materials, solar panels have a unique operational hazard. When they actively generate electricity, a state known as being charged, they physically preheat themselves. This chart compares the peak heat release rates of standard 4mm glass systems in both uncharged and maximum rated charge states. Charged 4mm glass shatters much faster, increasing the overall fire hazard by 60%. Testing reveals a physical solution. Upgrading the panels to thicker 6mm glass absorbs the heat and neutralizes this preheating shatter risk. A live solar panel presents physical risks that a dormant piece of glass does not, demanding a higher tier of engineering standards. Despite these risks, much of the industry still relies on traditional bench-scale flammability tests for safety certification. These small-scale laboratory tests are inadequate for this technology. They evaluate BIPV modules as if they were ordinary bricks, ignoring the complex airflow dynamics of a cavity wall. Standard sloped roof fine tests also fail to capture the severe intensity of a vertical facade flashover. BIPV technology is safe to deploy, but our historical testing standards fail to account for the physics of modern solar architecture. To secure these buildings, engineers must move away from testing individual panels and instead evaluate the entire BIPV assembly as a single unit. The cables, the insulation, the depth of the air cavity, and the glass thickness must all be evaluated together to guarantee safety. This holistic approach allows us to build net zero cities without compromising the strict safety requirements of high-rise construction. True sustainability is only achieved when visionary architectural design is backed by rigorous, uncompromised safety engineering.